The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
All right. So for this half of the course, we talked about chemical equilibrium, acid-base. We talked about oxidation reduction. We talked about shapes of molecules. We talked about this VSEPR theory. We talked about transition metals and kinetics, which we just ended on Monday. So all of these things represent the basic principles of how enzymes work. So enzymes work by acid-base catalysis. They catalyze oxidation reduction reactions. And so if we want to understand biochemistry, you need to understand these basic principles of chemistry. And that's how I got into chemistry in the first place, was this connection. And as I mentioned last time, inhibition of enzymes is an important area, and we need to understand how the enzymes work if we want to inhibit them. Well, why do we want to inhibit them? Well, inhibition of enzymes is used in the treatment of a lot of different conditions. So headaches, this time of year, a lot of us walk around carrying a bottle. You know, sometimes the small size isn't going to really quite do it. We might get a little larger. So here's ibuprofen. So there's a number of headaches that occur around now. And headaches are treated by inhibiting an enzyme. So someone has designed an inhibitor for an enzyme, and the enzymes are called prostaglandin synthases or cyclooxygenases. And these materials like aspirin and stuff bind to the enzyme and inhibit them. And to get good inhibitors, we need to know how the enzyme works. And so some of you have heard a lot of news recently about Vioxx. That was a drug that was designed to target the enzymes. And it was actually, they're very proud of themselves for trying to make the drug very specific to a particular type of cyclooxygenase enzyme, so it would only inhibit the class 2 and not 1. And it turns out that was a great idea, except that it was it turns out to be dangerous, or so. We'll see how that plays out. But all of that, they're targeting enzymes. Arthritis, a lot of drugs to treat cancer are inhibiting enzymes. I mentioned HIV, that they're inhibitors against the HIV protease, which is an enzyme. And so that people have designed inhibitors against that enzyme. So designing inhibitors against enzymes is a big part of the pharmaceutical industry. And to really have a good inhibitor, a good pharmaceutical product, you need to know a lot about how the enzyme works and also something about how the cell works so that you can make a good product. And this is big money. So understanding these basic principles then allows you to understand how enzymes work. So I'm going to take one enzyme, and I'm going to tell you about the enzyme. I'm going to tell you about how this enzyme works to do its reaction. And I'm going to use, in telling you about the enzyme, all of these things. So all of these different topics you need to know to understand this one enzyme. And if you understand these different topics, you will, in fact, be able to understand how this enzyme works. So the enzyme, shouldn't surprise you, is vitamin B12 dependent, my favorite vitamin. And it's called methionine synthase. And I've mentioned this a little bit in the course of the semester, and we're going to go back over some of those things as a review. So this is going to serve as a review of the different topics that we've covered, at the same time showing how these basic principles apply to other fields in chemistry and biology. So we'll start at the back. We'll start with kinetics. So that's easy. Methionine synthase, it's an enzyme. And enzymes are catalysts. And catalysts speed up reactions, make them go faster. And the speed of reactions, that's what kinetics is. So here's the reaction that methionine synthase catalyzes. It converts an amino acid called homocysteine into another amino acid called methionine. And it takes one form of folic acid, which is another B vitamin, and converts it to another form of folic acid. And this reaction is very important in your body. It's important for the proper formation and maintenance of your spinal cord. And women who are pregnant need to take lots of folic acid to make sure that they have enough for this reaction to go. So the baby is born with a properly formed brain and spinal column. So it's connected, inhibition is connected with neural tube defects. Homocysteine is linked with heart disease. So you want to make sure this enzyme is working really well, or you'll have too much homocysteine, and that's a big indicator of problems with heart disease. Also, you need this tetrahydrofolate, this one form of folic acid, for DNA biosynthesis. So some people have thought about inhibiting this enzyme to prevent this reaction, and that would lead to stopping cancer cells from growing. Of course, if they do that, they might cause people then to have heart problems. So there's definitely balances, and that's why the pharmaceutical industry often gets in trouble, because you solve one problem and then create another one. So you really need to know a lot about how the system works as a whole to be able to design good inhibitors. So this is a really important reaction. And so for this reaction to go in the body, you need a catalyst. You need this enzyme. So what do catalysts do? So this is a review of what we talked about on Monday. So catalysts act by lowering the activation energy barrier. So lowering EA, the activation energy barrier for the forward reaction, and also for the reverse reaction. So they don't change the overall thermodynamics, they don't change delta G, they don't change the equilibrium constant, but they do speed up the reaction by lowering this barrier. So there's a much higher barrier without the catalyst, lower barrier. It stabilizes, another way to think about it is it stabilizes the activated state or the transition state. So catalysts don't take part in the they're not in the overall equation, they're not consumed in the reaction, they're just added to make the reaction go faster. So that's a catalyst, and enzymes are the catalysts of life. Transition metals. So we're moving backwards through the semester. Transition metals, this one, lots of transition metals, uses vitamin B12, which has cobalt, and it uses zinc. So here is the methyl form of vitamin B12, also called methylcobalamin, and it has a corin ring. The corin ring contributes 4 nitrogen ligands to the central cobalt. So it is a tetradentate ligand, and that tetradentate ligand coordinates the cobalt. It is a chelate. And so we can review what the chelate effect is. So chelates have, a chelating ligand has multiple points of attachment to the particular metal, and they're unusually stable. Why are chelates unusually stable? What factor is it that causes that unusual stability? It's entropy. So it's entropic effects, because usually you're replacing 4 bound waters in this case with 1 ligand. So you're putting one thing on and releasing 4. And it's easier for 4 things to be disordered than for 1 thing to be disordered. So that gives you a favorable entropic effect. So the chelate effect has to do with entropy. So now let's consider the zinc. It also needs zinc for this to work. So zinc plus 2. What would be the D count? How many D electrons are you going to have? So for that, we would go to the periodic table, find zinc, and see what groups it's in. It's 12. The oxidation number is 2. So we're at 12 minus 2, or a D10 state. What would you guess would be the color of this zinc site? Colorless. And that's because you're not going to be able to have any D to D transitions, because you have 10 electrons, everything's full. So there are 5 orbitals, and they all have 2 electrons each, So it's completely full. So you would have a colorless system. Now, people didn't realize methionine synthase was a zinc enzyme for a long time. Vitamin B12 has a beautiful red color, and zinc had no color. So they knew it was a B12-dependent enzyme, but people were studying this enzyme for years and years and years before they realized that zinc was bound to the protein because it has no color. Okay, so what about VESPR? VESPR allows you to predict or rationalize shapes of molecules based on a simple idea of repulsion, that lone pairs want to fill up space and move the bound atoms away, that there's sort of the structure is designed such that there's minimal repulsion between bound electrons or electrons in orbitals. So if we consider this then, if we look at the steric number for the whole center around the cobalt, and again, there's this tetradentate core and ring system, and there's one ligand above and one ligand below. And so what does that give for our steric number? 6. So we have 4 around in the equatorial positions and 2 in the axial positions. What formula would this be? What's first? A, then X, then 6. Yep. So we have a central atom A, and we have 6 things around it. And what would be the geometry of something that had 6 things around it? Octahedral. And here we have our octahedral system. So if I hold it like this, the equatorial positions are filled with the core and ring, have a methyl group on top, and we have another ligand on the bottom. What are the angles for octahedral? 90. Thank you. All right, the zinc site. I'll tell you a little about the zinc site. 3 ligands were identified to zinc. And so geometry is going to have X equals 3. We might know, if you don't know what the ligands are, might not know about lone pairs. But if you have 3 things bound, what's the most common geometry if 3 things are bound? Yeah, trigonal planar is pretty common with 3 things bound, so that might be a good guess. And so it might look something like this. And what would be the angles if that was the correct geometry? Right, 120. Okay, so we know something about it from VESPR. All right, oxidation reduction. This enzyme catalyzes an oxidation reduction reaction. So here is the cycle of turnover for this enzyme. So we have a lot of different reactions going on in this enzyme. So here's an abbreviation for the cobalamin cofactor. So we just have the cobalt and its oxidation number of 1 here. And sometimes, instead of going around in this primary turnover, its normal sort of cycle, where it's reacting with the folic acid and reacting with the homocysteine, instead, sometimes an electron is lost. And for it to kind of come back into the catalytic cycle, the enzyme needs to be activated. And so it falls out, it becomes COB2 state, it loses an electron, it becomes oxidized, and then you have to re-reduce it, and you have to methylate it to go back into this form. So the methyl group, and a methyl is just a carbon with 3 hydrogens, the methyl group comes from this compound called acetylmethionine, and it gets an electron for the reduction from flavidoxin. So if we look at this oxidation reduction, and we talked about this a bit earlier too, but it's a really nice review for oxidation reduction. So we have a standard potential for vitamin B12 of minus 0.526 volts, and a standard potential for flavidoxin of minus 0.23 volts. So which of these is a better reducing agent? B12 is a better reducing agent. So a large negative reduction potential means that the reduced species is very reducing. So if it's a good oxidizing agent, it likes to oxidize, a good reducing agent, it likes to reduce other things and be oxidized itself. So B12 has a low negative number. So with this, if we do the math here and calculate a delta E for the cell, and again, the same equations can apply if you're talking about a battery or you're talking about a biological process. So we have the standard reduction potential for the reaction that is a reduction, and the standard reduction potential for the reaction that's acting as the oxidation. And in this biological case, flavonoxin is reducing vitamin B12. So flavonoxin is getting oxidized and B12 is getting reduced. And if we put in the numbers, we find that delta E is minus 0.296. So is that going to be a spontaneous reaction? No, it won't be a spontaneous reaction. Because if this is negative, if delta E is negative, then delta G is going to be positive. And if delta G is positive, then it's not spontaneous. And we did this, this math before, but just as a review, you can calculate delta G if you know the delta E. So it's just minus the number of electrons involved times Faraday's constant times your delta E, your change in the cell potential. So that would be minus 1. It's a 1 electron reduction times Faraday's constant times the cell potential we calculated, and we get positive 28.6 kilojoules per mole. So that's not spontaneous. But as I mentioned, the cells come up with a way to do this. It has to do this reaction or none of us would be alive. This is an important reaction for us. So the way that it does that is it couples it with another reaction. So at the same time the reduction's happening, you're cleaving that S-adenosine methionine. It's giving up the methyl group, which is important for the reaction. But also this is very favorable, minus 37.6 kilojoules per mole. So that allows the reaction to go. That sort of pumps in the energy that's needed for this unfavorable oxidation reduction reaction to occur. So cells that require energy to catalyze non-spontaneous reactions are called what? Right, electrolytic. And if it's a spontaneous reaction, it's what? Galvanic, right. So here in this one example, we talk about the connection between thermodynamics and oxidation reduction, and we talk about oxidizing agents and reducing agents. All right, so the enzyme does an oxidation reduction. It's a catalyst. It speeds up the reaction. It has 2 transition metals in it. And it uses acid-base catalysis as well. So let's talk about acid-base. So there is an acid-base reaction. There's catalysis by a Lewis acid in this part of the reaction. The reaction with homocysteine, the conversion to methionine. So let's talk about this. So the B12 is going to give up this methyl group to homocysteine to make methionine. So it turns out that only the deprotonated homocysteine is reactive. So here is homocysteine. It's an amino acid. This is protonated. The sulfur down here has a proton. This is deprotonated homocysteine. The sulfur here has no proton. It has a negative charge. And only this homocysteine here that's deprotonated with the sulfur with the negative charge can be methylated. The reaction catalyzed transfers this methyl group, the CH3 group, and puts it on the sulfur. And that makes the amino acid methionine. But if there's a proton there, the methyl transfer doesn't happen. It has to be deprotonated. So at physiological pH, we need to ask the question, how much homocysteine is deprotonated? Remember, our body is buffered. It's all around the same pH. So we want to know, at this pH, how much of the homocysteine is in the deprotonated form, and how much of the homocysteine is in the protonated form. What do we need to know? What value do we need to know to be able to answer at a particular pH how much HA do you have and how much A- do you have? What do we need to know? we need to know the pKa. So question, what is the pKa? And here, it's 10. So that is a big number. So if we know the pH, physiological pH, we know the pKa, what equation can we use to find the ratio of HA to A minus? Henderson-Hasselbalch. So we can do the math. So physiological pH is around 7.4. The pKa is 10. So what is the ratio of protonated to deprotonated? The ratio of this protonated homocysteine to the deprotonated. And turns out to be 400 protonated for every 1 deprotonated. Well, that's bad news for us because it needs to be deprotonated to be reactive. So at physiological pH then, it's protonated and non-reactive. So here the enzyme has to come in. Enzymes catalyze reactions. The enzyme needs to get involved and make this reaction happen. So again, this is unfavorable without the enzyme. So let's think a little bit about pH and pKa for a minute. So let's review some acid-base titration issues. This isn't in your handout, but I don't think, but it's been there before. But let's just take a look at it. So you should remember what these titration curves look like. Remember, at the half equivalence point, pH equals pKa. And when that happens because at the half equivalence point, half of the acid has been converted to the conjugate base. So these are equal quantities, and so they'll cancel out in the Henderson-Hasselbalch, and this will be true. So you have equal amounts. If you're at a pH that's below the half equivalence point, you'll be more protonated. If you're at a pH that's above the half equivalence point, you'll be more deprotonated. So we haven't maybe discussed this in these terms, but that's how you can think about this problem. So now let's go back to methionine synthase, and this is in your handout. So at the half equivalence point in a titration, or when the pH equals the pKa, half of your material is protonated, half of your material is deprotonated. If your pH is below that pKa, you're more protonated. If you're a little bit below, you still have some deprotonated. If you're very far below, it's all protonated. Going the other direction, if you're at a pH above the pKa, you have mostly deprotonated, maybe a little protonated, and when you get far away, it's all deprotonated. So now we can put in what we know about homocysteine. So the pKa is 10, and we're at pH 7.4. So we're quite a bit below the pKa, and we calculated that at that pH, with this pKa, we'd have 400 protonated to every 1 deprotonated. So didn't write out 400 of these to be protonated for every 1 deprotonated, but we're mostly protonated. All right, so that's the problem, because we don't want to be protonated, we want to be deprotonated for the enzyme to work. So what does the enzyme do? Well, part of how the enzyme catalyzes the reaction is that it lowers the pKa of the homocysteine. So instead of 10, which is what the pKa is with free homocysteine, the pKa now, when homocysteine is bound to the enzyme, is 6. So that's a pretty substantial drop. So the pKa is substantially lowered. So now let's go and look at what that does for us in terms of the reaction that's catalyzed. All right, so what's happening here is the zinc. Here comes the zinc. The zinc is acting as a Lewis acid, and it is coordinating, binding that homocysteine. And that interaction between the zinc and the sulfur of the homocysteine lowers the pKa of the homocysteine from 10 to 6. So that's why this protein has to have the zinc to act as the Lewis acid. So we can go back to Henderson-Hasselbalch and plug in our new values. So we're still at physiological pH, 7.4, but now the pKa is 6. And so our ratio then of protonated to deprotonated, instead of 400 to 1, is now 1 to 25. So there's more deprotonated homocysteine when it's bound to the enzyme at this physiological pH because the pKa is lower. And if we look at that in terms of this, again, here's the pKa. The protonated is equal to deprotonated. And our pKa now is 6 for the bound homocysteine. And now the pH, the physiological pH, is above the pKa. It's at 7.4. And above the pKa, there's more deprotonated, 25 deprotonated, to 1 protonated. So now we're in good shape. You need the deprotonated for it to be reactive. Most of it is deprotonated. The enzyme can go. So the enzyme uses this Lewis acid catalysis to drive this reaction forward in the direction that you want. So it's all about adjusting. Enzymes can work by adjusting pKa's. All right. Chemical equilibrium, the first thing we started with in the second half of the semester. So what's true about methionine synthase is that it exists in multiple conformations. This enzyme can have multiple states. And these conformations are in equilibrium with each other. So lots of things can be in equilibrium, including enzymes. And equilibrium is a dynamic process. So what's happening? Well, let's look at why this enzyme would need multiple states. Well, it needs to react with homocysteine. It needs to react with the folic acid. And it needs to react with the S-adenosylmethionine and flavodoxin to do this reaction over here. So if we look at the structure of the enzyme, the vitamin B12 is in green. The methyl group that's going to be transferred is in red. And all this yellow and white is more protein. So homocysteine, when it's deprotonated, needs to come in here and accept that methyl group. Folic acid needs to come in here and donate the methyl group. And also S-adenosylmethionine in the activation reaction needs to methylate. At the same time, the electron is added to the system. So the enzyme needs to position all of these guys up here. And if you look at the structure, there's no room for anything to fit into the structure. Nothing can kind of go over. You can just barely see the methyl group. But these guys are kind of big, and they're not going to fit in here. Because in this one conformation of the enzyme, they don't fit. So the answer has to be that the enzyme moves. It changes shape during the reaction. And this is something that had been known for enzymes, that they did this for quite some time. But my father told all our neighbors that his daughter had discovered that enzymes change shape. But since none of our neighbors knew anything about biochemistry, even what an enzyme was, I think that that was just fine. All right, so this needs to change shape. So this is a picture of the structure. Here's the B12. The red is the methyl group again. So this whole region needs to move to make room for those reactions to happen. So there's got to be a number of different states of this protein. So here's a little cartoon. So in orange is where the B12 binds to the protein. The B12 is in red. This region above we call the methyl cap. It sits over the methyl group and protects it. There needs to be a domain to bind folic acid. Another domain binds homocysteine. And another domain over here binds the S-adenosylmethionine and is involved in that oxidation reduction reaction and the remethylation. So what has to be true for this enzyme is that you need at least 4 different conformations. You need a conformation where the folic acid sits on top of the B12. It needs to give the methyl group over. You need a conformation where the homocysteine in yellow domain sits on top of the B12 and accepts the methyl group. Zinc needs to be around there too. You need a conformation that's resting, where the region that we saw in the initial crystal structure is sitting over this cap, is capping the B12. And you need a conformation where this activating domain is above the B12 to do the oxidation reduction reaction there. So we need at least these 4 conformations. And what's true is that the enzyme is just kind of switching conformation as it's going through, and that these conformations are in equilibrium with each other, and they're just shifting back and forth to these different states. And when you add something like folic acid, it helps shift the conformation to this form. When you add homocysteine, it helps shift the conformation to this form. So this is just chemical equilibrium going on. So there's a lot of things that can be in equilibrium, and enzyme conformations can be in equilibrium, just like some of the reactions that we studied in the beginning of the course. So enzymes are dynamic. Equilibrium is a dynamic process. Chemistry is dynamic. Things are happening. I'm not talking about chemistry in the solid state in this course. I am talking about chemistry in solution, because that is chemistry of life. That's the chemistry that's happening in your body that allows you to breathe and live. And so finally, I'm going to show you methionine synthase in action in its dynamic process.